All right, everyone, we can begin. So before we jump into the talk, I'm just gonna quickly introduce what exactly this is. So this is part of the CANSSI Ontario Statistics Seminar Series, known as the CASS series. So CASS spotlights groundbreaking research in both statistical sciences, both applied and theoretical, from Canada and around the world. The goal of the CASS seminar series is for participants to engage with leading experts and deepen their knowledge on statistical research. So this seminar is in collaboration with both the University of Waterloo and CANSSI Ontario. The goal of this is CANSSI's goal is to advance research and training in statistical sciences by developing programs that both promote interdisciplinary research and enable many collaborations. So I'm now going to introduce our speaker for today. So today we have Dr. Marcel Nutz from Columbia University. He is part of the statistics department there. He's also affiliated with the Department of Mathematics and the Data Science Institute there. His research focuses on quantitative finance and optimal transport and the connection between them. His work has been recognized with an IMS Medallion Award and an Alfred P. Sloan Fellowship. He is also an IMS Fellow. So today, he'll be talking about sparse regularized optimal transport. And can you all join me in welcome him to the
The owl's got it. You know, the owl's got it, but you have a strong voice. I don't. You're going to consider. Okay, thanks so much for having me. It's a great pleasure to be back. Yeah, briefly, I think we were the most famous university in the US. I think now Harvard is back at the top. I realized this statistics seminar, at least that's what I read. So I chose the most statistical project I have. It's pretty much completed. So we're about to submit it this week. So it's about some statistical questions in optimal transport. There is no finance anything in this talk. And yes, please interrupt me with questions. How many of you are vaguely familiar with optimal transport? Just to get. Who has never heard of optimal transport? Okay, so I'll assume, okay, this joint work with Alberto Gonzalez-Sanz, who's a postdoc at Columbia, and Stephan Eckstein in Tübingen. Actually, mostly this guy, he's like 90% the author of this. Okay, so there are three parts. Only this, half of this is the paper. So if you haven't heard, maybe it's good, there's some very general introductory stuff about optimal transport, some stuff about entropically regularized optimal transport, which if you don't know anything about it, then it's just going to be good for your general education. And otherwise, it's about sort of setting the stage for what we're doing and to contrast what we're doing. And then this is going to be about our stuff. Okay, so what's optimal transport? What's the basic formulation? So in this talk, X and Y will be some compact subsets of RD. Doesn't really matter too much what they are for now. And there will be two probability measures, mu and nu. Those I'm going to refer to those as the given marginals, so they're going to be fixed. And then the other ingredient that's given to you in optimal transport is a cost function. So it's a function of X and Y into the real numbers. Okay. And what it tells you is if you want to move 1 unit of mass from a point X to a point Y, how much you have to pay for that. So you imagine mu is some shape, mu is some shape, and your goal is to transform one shape into the other. So Mosch was a French dude who went 300 years ago, and he had some interesting jobs, including he was naval minister. So he was interested in military installations where the interest was actually in moving dirt to build like fortifications and so on. Okay, so this is the mathematical problem. Mosch is looking for a map from X to Y, which pushes mu forward to nu, or probabilistically, if you take mu as your base probability and see t as a random variable, the distribution of t under mu should be nu. That's the given constraint. And what it means pictorially is actually transform this shape into that shape. So there are hopefully one or more maps T that actually achieve this. And then you look at the set of all them and you minimize this functional over it. What's dysfunctional? Dysfunctional says that for every x in the support of mu, you pick up the mass from x, you bring it to t of x, which is a y. Per unit mass, you pay the cost c, and then you sum up over the whole x space. Okay, so this is going to be the total cost of bringing all the mass into its destination. Okay, this is what we're minimizing. So that's motion solving transport problem. Interrupt me if you have a question. All right, so this is a mathematically somewhat difficult set, this set of transport maps that achieve this. That's why this, okay, sorry, that's another slide here. So for introductory talk, this is the so-called assignment problem, which is a special case. It's a special case in which the two marginals mu and nu are uniform measures on endpoints each. Okay, so you have endpoints xi, endpoints yi. What is a transport map in this case? It's just a permutation of the indices. Okay, if you want to have a map from the x's to the y's, it just means that for each xi, you have to find one yj where you're going to transport the mass to. Okay, so you can think of it as an assignment, which is why this problem is all over economics. And you're assigning jobs to workers, or there's a huge literature in so-called marriage problem where you assign men to women, and so on. Right? So in this context, a transport map is a permutation. What you have to do is you have to bring each point to one point. What you're not allowed to do is you cannot cut a point in two and assign it to two, which is very meaningful in the marriage problem, but less meaningful in some other problems. So the Kantorovich relaxation of Moshe's problem allows you to do exactly what I just said. So in the relaxation, you are allowed to cut the mass into pieces and distribute into several destinations. Okay, so this is thought of as a randomization. Okay, so mathematically, the formulation is following. You're no longer looking for a map. You're now looking for a coupling. So it's a probability, a joint distribution of the product space, whose first and second marginals are the ones that are given. And then the cost you're minimizing is this thing here. So you just minimize the integral of c with respect to the coupling time. A coupling is a generalization of a map as before, namely corresponding to those couplings that have a disintegration with respect to the first marginal, which is the Dirac, right? So conditional on x, all the mass has to go to t of x. That's what this means. And of course, if you add up several such kernels, or you take convex combination of such kernels, it corresponds to splitting mass, sending into several destinations. Right? So in the space of measures, when you take convex combinations of maps seen in this way, you end up with a margin. And indeed, this is just a closed convex hull of what we've seen before. So this is a very natural convexification of the problem. Right, so now you're minimizing, this is linear with respect to pi, you're minimizing over a convex set. So now this is a nice problem. And generally, when you convexify in a problem like this, you don't really increase the value. In many cases, it's sort of intuitive that this is somehow attained at the boundary, right? When you have a linear objective over a convex function. So what does the boundary, what do extreme points look like? They probably look roughly like maps. Indeed, in many important examples, when you solve this problem, it has a unique solution, and that unique solution actually is a map, like on the previous slide. But still, for the math, it's usually much more convenient to start with this relaxed problem, which is why after Kantorovich, there has been a lot more progress in optimal transport than before. Okay, why would you care as a statistician? Most of the time because you want to compare two distributions, or maybe something empirical, data and a reference distribution. How does optimal transport come in? You can look at the transport problem for two marginals. So you look at this number here, given to these two distributions, what is this? What is the optimal cost? And think of it as a dissimilarity measure for suitable cost function C. The most important examples are when x and y are the same space, and you take C to be the square distance, right? Then the optimal cost to bring mu to nu with a square root on top of it is the so-called two-Wasserstein distance, and is a very convenient way to say how different two distributions are. And I guess in the last 10 years or so, most people in at least my statistics department kind of know optimal transport. For that reason, it gives a, has a nice geometry and plenty of applications. The optimal transport problem is fairly rigid, and you see it in several ways. One of them is in its sample complexity. So, okay, there's a vast literature on studying sort of the statistical complexity of that problem. That could be by general, what kind of estimators can you find, and so on. So here I'm interested in just a simple plug-in estimation. Okay, so here the problem is the following. We're going to have i.i.d. samples from the first marginal mu. I'm going to have i.i.d. samples also independent from the second marginal mu. Okay, now we have two empirical measures, and we can look at the optimal transport between the two of them, which happens to be actually a special case of the assignment problem, right? Because now it's random, but whatever. For each realization, you have one uniform measure on endpoints and another uniform measure on endpoints, and then look at this optimal transport problem, right? So then you just plug in, and this intuitively should be an estimator for the optimal transport problem that we started with. So for this, it's known that the sample complexity is this. Okay, so if you look at this plug-in estimator, how fast does it converge to the population quantity? Somewhat generally, if mu is not equal to nu, this is the rate, and this rate is sharp. If mu is equal to nu, then this 2 is a 1. But the main thing here is the d, so it's very dimension dependent. It deteriorates exponentially with the dimension, which is what you should call the curse of dimensionality. Okay, and this is some embodiment of the fact that this problem is quite rigid. Sorry, it's true when the dimension is not too small, the lower dimension is part of it. Okay, and maybe similarly, the computation of the problem is relatively difficult. In the best case, which is the assignment problem, the cost is n to the n cubed. So this kind of tells you how many more points you need to take as your dimension increases if you want to have a given precision. And then this is how much the computation will cost. Questions so far? Okay, so much about OT problem. Okay, so there are many approaches to try to circumvent this curse of dimensionality by either redefining the distance, smoothing it out, measuring it only in one-dimensional sections, or by regularizing the problem with a penalty. Okay, the last solution is the one I'm going to be interested in. Okay, and the most popular, by far, most studied way of regularizing this problem with a penalty is by adding Kullback-Leibler divergence or relative entropy. Okay, so what's on this slide here? The entropic optimal transfer problem is the exact same Kantorovich problem that we just saw before. And then there is a parameter that you choose and fix, epsilon, and the KL divergence between the coupling under consideration and a reference measure. And the reference measure, we usually choose it to be the product of the two marginals. Okay. You're probably familiar with the KL divergence, which you can compute as the log of the relative density integrated with respect to the first argument. Okay. Later, we're going to be interested in putting also other divergences there. In general, all of these have the property that this is something non-negative. It's strictly convex in the first argument. It's 0 if and only if the first argument equals the second argument. Okay, so it measures how similar or dissimilar these two things are. Okay, so here, what did we do? We had a linear problem in pi. We added something strictly convex. So together, it's strictly convex. This problem has a unique minimizer, even if the OT problem had a non-unique one. If you set epsilon to 0, obviously this is gone. You recover the problem from before. In general, epsilon will somehow give you the strength of the penalization or regularization. When epsilon is close to 0, you basically solve an optimal transport. When epsilon is big, you start caring more about this than about this. And so it's going to be a trade-off between the two. This is minimized when pi is equal to the product here, which is actually a coupling. So the solution is going to start to look more like that. And when epsilon is small, your solution is going to look more like the solution of this. Okay, just to illustrate this, I think I have a picture. Yes. So here, what are we doing? The mu and nu are the red and the blue density. They're actually here on the real line, right? And we're looking to couple them. 10 is a very large regularization parameter. You can see the solution looks roughly like the product measure. And here we're making epsilon smaller and smaller. And well, I should tell you that for this particular setup, and this is for the quadratic distance cost, the solution of the unregularized optimal transfer problem is unique and is given by a map, the so-called Bernier map. So if you think about it as the support should just be a line, a graph, and you can indeed see that the coupling starts to look that way. Okay, so it starts to concentrate very much close to the optimal transport when epsilon is small. There's 1/100. Okay, so there's some of the protagonists that are used and come up in this talk. Whenever you have a convex problem, you should look at the dual problem as well. Okay, the dual problem roughly are the Lagrange multipliers for the constraints in the primal problem, if you have not seen any linear program. Here, okay, so in quite a few, but not all of my slides, this regularization parameter epsilon, and I'll take it to be 1 to have simpler formulas. As long as you're not changing epsilon, that's sort of without loss of generality. Why? Because you can just divide everything by epsilon, then this epsilon becomes a 1, and here just C is replaced by C over epsilon. But as long as C is general, that's fine, right? Still covers it. And then here you just apparently scale. Right, so take epsilon equal to 1. Then the dual problem is this one here. So the dual problem is a maximization over 2 functions, which here I can take to be continuous. Okay, so these 2 functions correspond to the fact that in a parallel problem, you have constrained the marginals mu. And you compute it in this way. So here's integral with respect to the product measure. So basically integral of f with respect to mu, integral of g with respect to nu, and then this crucial part here minus e to the f plus g minus. You will always see f plus g minus e in the top. All right, so this has a essentially unique solution. It's non-unique in the sense that you can always like add a constant to f and subtract the same constant of g because f plus g is everywhere. That's not going to change anything. But apart from that detail, it has a unique solution. This solution is called the potentials, Schrödinger potentials, and they're important in many regards. One of them is that knowing the primal solution pi is the same as knowing the dual solution because they have this relationship here. So exponential of f plus g minus cost gives you the density of the optimal coupling, and vice versa. You always have this decomposition of the log density. Okay, so this problem has a first order condition of optimality. Essentially, the derivative should be 0 at the optimum. Okay, that gives you a system of equations, which is called the Schrödinger system, or whatever you want to call it, which is these 2 equations. I guess another way to think about those equations is that coming from here, so if you remember the formula for the marginal density of a joint distribution, it's actually this integral. So this kind of says that the marginal density is 1, which it should be because it's a coupling. Okay, so this another way to think of it is if you take as a given that this is the density of a probability measure, then it's going to be a coupling if and only if those 2 are satisfied. It's going to have the correct marginals in that case. Either ways, so because the exponential is the exponential, you can write this as e to the f plus e to the rest, right? And then actually, because this is the x integral, you can take the e to the g of y to the other side, and similarly here. So you can actually solve this sort of for f and g, which has some nice consequences. One is if you wanted to solve this, okay, the most naive thing you can do is you can do the Gauss cycle iteration where you just say, okay, let me initialize, for instance, f to be 0, and then I just plug my 0 here, and I compute the right-hand side, and I get a new g. Then I take that g, I plug it in here, I compute this, I get the new f, and then I plug it in here, and then I go further back and further back, and if I'm lucky, I'm going to converge. Okay, that's called the IPFP, or Synchron's algorithm, which is exactly what I just said. Okay, that's one of the approaches, probably the most popular approach, especially in the high-dimensional setting. As you can see, this is very easy to implement. You just have to do a matrix vector multiplication if you're in a discretized setting. So this can be computed very well. There are several interpretations to this algorithm. The one I gave is a bit naive. One that is kind of nice is this block coordinate ascent point of view, where G, okay, it doesn't really matter what it is, but let's call this capital G, whatever is the objective you have there. So what you can think about is, let me, it's hard to do the joint optimization in F and G. Let me freeze one and just optimize the other. Okay, so you can do that again, start with F equal to 0 and just maximize with respect to G. Turns out what you're doing when you're solving that problem has explicit solution, and this is the explicit solution. So given F, T, this is the best thing you can do in G. And similarly, if you freeze G, this Ft plus 1 is the best thing you can do here. So you have closed form solution for the individual maximization. So then you just keep doing this forth and back and forth and back. It's kind of meaningful that you should actually converge to the optimizer in that way. And in fact, in the optimization community, it's well known that if you're doing this with a strongly concave function, which this happens to be, when you have uniform bounds on F and G, which you do in this case, thanks to the properties of the exponential. So when you do this with a strongly concave function, then you will automatically have linear convergence of this algorithm to the unique optimizer. Linear convergence means exponentially fast convergence, thanks to the optimization terminology. So it has like a geometric kind of rate. Yeah, it's always confusing. Why you say converges linearly? How it converges exponentially? It's like, well, anyway. Okay, so that kind of, this strong concavity is kind of important in this context. That's one thing I want you to remember. And also for your general education, there's this nice algorithm, which is heavily used. Another consequence of that system, let me flash it again, either this one or this one, is maybe this one. It immediately tells you something about the regularity. So here's another way of writing that equation. Well, or even the other form, doesn't matter. If you wanted to compute the derivatives here of f or of the left-hand side, you can just take them under the integral here, right? So suppose your cost C is smooth, and I tell you that f and g are at least continuous, then this gives you formulas for all the derivatives, right? So actually f and g have to be as smooth as the costs because of this particular convolution kind of relationship. Okay, so that's very powerful, and you can do it a little bit more concretely, that you really get to control the uniform norms of all the derivatives using C. Okay, so you'll get something like these, that given the cost function C, and remember x and y are the given compact sets, if C is smooth, then the CK norms, so these are the uniform norms of the functions and its derivative up to the kth norm order, can be dominated by some constant. And this will only depend on the cost function. It will not depend on the mu and nu. So it depends on the x and y, but not on the mu. So that's going to be quite important. Okay, why is it important? So I'm trying to talk about sample complexity of regularized optimal transports. Here is a well-known result, and in fact, well-studied area. Here is the first result. So remember what you're doing. We're taking i.i.d. samples from the first marginal and from the second marginal, and then we solve the assignment problem between the two, which is basically the plug-in optimizer estimator for this problem, right? And here we're looking at the expected absolute difference. And before, when we did the same thing for optimal transport, this was the n to the -2 over d. Whereas for the entropic optimal transport, this is the parametric rate, it's dimension independent. Okay, this completely went away. Okay, so for EOT, there's by now a large literature, which is okay, all in the last 5 years, but has looked at this in great detail. Here, constant hidden, whatever. But now there are like these results for the cost, which is the one here, for the potentials, for the couplings, there are even CLTs for these objects. People know quite a bit about what's going on with the constants and so on. It's mostly for smooth cost. There's also an alternative approach. In fact, this paper here of Riegel and Ströme, which is about possibly non-smooth cost. And here, let me say something about the proofs. The first approach uses the regularity of the potentials. So roughly speaking, if you want to have sample complexity of the optimal cost. The optimal cost is equal to this dual that comes from out of duality. Okay, so here generally, forget the soup for a moment. You suppose you have some nice expression here, some nice continuous function, and then here you plug in the empirical measures, which are right. So the sample versions, right? So then you want to have some sort of Plimenko-Cantelli. If you had just one function here, then sort of standard theory gives you the parametric rate. And generally, with this kind of functional, the issue is that when you take the supremum over a large class, then you can screw up the parametric, right? And that's why in general you will have, for instance, dimension dependence, because dimension is kind of about how big this class is. Okay, so the lucky case is the following. If you can reduce this class to a smaller class, okay, then maybe you're good. And so, because here, as I said, we know a priori that we can control the CK norms of f and g. We can actually reduce this supremum to one of f and g with CK norms, less than constant, independently of the mu and nu, which is important because we want that also for the empirical versions. Okay, so in general, what you want is you want to be able to pick k larger than dimension over 2. And if you can bound that norm, then that makes the set here small enough so that here you will still get the parametric rating. Okay, so that's how the game works for the EOT. When the cost is not smooth, you can't do that. So there's something completely different being done in Regularize paper. Regularize paper uses the PL inequality, which is based on the strong concavity of this problem. Okay, what's the flip side? So EOT, everything is wonderful and smooth. Really, it's much more, better behaved than the unregularized optimal transport problem. The flip side of it is the following. So you've observed in the formula for the density, it is exponential of something. So it's always positive. Exponential, it can't help. It has to be positive, right? So the optimal coupling in entropic optimal transport is always equivalent to the product measure, in the sense that it has the same null sets. So if you think about the support, the full, those pictures with the x and the y, the full square is always going to be the support. Okay, it's unavoidable. I mean, this is just a formula, but it really comes from the fact that the x log x function, which defines the KL divergence, has the infinite derivative at 0. So you always want to go away from 0 and put a tiny little bit of mass everywhere. So maybe that was not emphasized here, but when I look at these pictures, so here where it's white, it's actually not white. There's a little bit of mass everywhere in this picture, for even when epsilon is very small. Okay. And that is kind of linked to this whole smoothness and everything. Okay, so you always have full support. And it's curious because, right, you're approximating the optimal transport problem. The solution of the optimal transport problem in most practical examples is actually given by a map. So it means the support is a graph, right? It's d-dimensional subset of 2D-dimensional space. So the limiting object here is sparse. If you think about the support, really as sparse as it can be. There's no, as a coupling, you can be more sparse than a graph, really. But the approximation, if you think about the support, it has this huge discontinuity where it goes from the full space to the sparse thing just at the limit in a jump kind of way. In applications, what does that do? It often amounts to some sort of overspreading or blurring of things. Add a picture for this. So, like, you can use optimal transform to deform, cute pictures like a ball with, I don't know, different colors, right? Some here, something here, and maybe some other shape. Right, and that should be good with this. Yeah, you could compute optimal transport from here to here, and it would define a very nice map that actually transports the boundary to the boundary, and this kind of like this. And then you could deform this into this, and everything in between, even that I'm not drawing, would look kind of similar. Okay, you can have this very good pictures. Now, what does it mean if you use the approximation, which is given by entropic optimal transport? A little bit of this color is going to be everywhere, right? Because every origin point here will be, this point would go mostly here, but it's a distribution, and a little bit of it would end up splattered over the whole picture. So for image processing, there's going to be a little bit of a blur. Or in other applications, for instance, in manifold learning, it kind of means that you don't quite stay on the manifold. You can like cross through the space where you're not supposed to cross. So it's often a problem in applications, what you do with that little mass that you have somewhere. Of course, you can sort of just truncate it away, or what is better, you take the conditional distribution and replace it by its expectation, so-called barycentric projection. So these are ways to actually get sparse objects. But when you do that, you're not really a coupling anymore. So there's no easy way to preserve the coupling property and sort of, remove that little mass. Okay, so that's sometimes a concern, and there's no easy solution in EOT. So there's some interest in, can I do something similar that will actually produce a sparse solution? Sparse in the sense that, the support is not going to go far away from the support of the optimal transport. Okay, so that's our starting point. And we kind of know that, the smoothness is related to this, so it's not going to be as smooth. Yeah. Okay, questions so far? Okay, so here's the sparse stuff. How we can get something sparse is by changing the regularization into something different. Okay, so in general, the regularized optimal transfer problem will be exactly the same as before, but instead of put like Liber divergence, we put some other divergence or other name. Okay, in general, the so-called f-divergences, sorry, I have to take phi because f is busy, are defined in this way. You integrate phi of the density with respect to the second argument. Okay, so to get the previous one, it's x log x, because I'm integrating with respect to the second one, not the first one. In general, we are going to be interested here in convex functions phi. And the prime example, they go under the fancy name of Tsallis divergence, but it just boils down to using the LP norm of the density as a regularizer. Okay. The constants can be written in different ways, for instance, p minus 1, but actually constants don't matter anyway. So if you evaluate this, then you realize that this integral is going to be the LP norm of the density to the power b. Okay, so especially the p equal 2 will be the chi square, or the quadratic regularization where you take the squared L2 norm of the density as a regularized. So you try to, regularization is one which penalizes very large values of the density, and therefore will, smoothen out the coupling a little bit. This has been used in a couple of papers. Most of the existing literature is either applied or computational. When I first learned about this, the message I was given is it works computationally, and you cannot prove anything. Okay, so here's an illustration for the sparsity. This is for the p equal to 2. So at the top, this is actually the density, and this heat map would look visually very similar for entropic regularization. Okay. But the bottom is the actual support. So green is where you have mass, and black, there is no mass. And here you can see that this is actually 0 and 0 and 0. And here, really, the support is sparse. So this is a simple example where the cost is quadratic, and both marginals are uniform. So the solution is just identity map, and this is the support of identity map. Okay, whereas if I did this in entropic case, it would just be all green. Okay, is it clear what's different? Just a way of rounding away that part. Okay, there are some theoretical results very recently. Funny enough that somehow there was nothing in the literature. So roughly what we're trying to say is that take the quadratic cost, marginals with densities. Okay, here's two things. So in the discrete case, for instance, for quadratic regularization, the following is true. Discrete case means the marginals are discrete. If you make the regularization parameter small enough, then actually the solution of the regularized problem is equal to the solution of the optimal transport problem. This can never happen for entropic regularization because support is always going to be completely different. Okay, but for quadratic, that actually happens. Of course, the threshold is going to be very small as the number of points decreases. In the continuous case, again, it can't happen because the solution of the regularized problem has to be absolutely complete with respect to the product measure, and the solution of the optimal transfer problem usually isn't. So the statement of sparsity is something of the type, take the support of the limiting of the optimal transport, the unregularized one, which is usually a graph, maybe, make a sausage around it, hopefully small sausage, does not capture the support of the solution coupling when epsilon is small. So that's indeed true. And then maybe you want to say how big that sausage actually needs to be. And we believe it needs to be epsilon to the 1 over d plus 2. But really, we have proved it will be the one-dimensional case and some other special cases, including where mu equals c. There are actually quite a few open questions about this. Intuitively, you would expect that the support is kind of monotone in epsilon, growing. And maybe in the exponent also, if you choose the right normalization. For the first part, we have a result, but not for the second. Anyway, so I'm trying to go towards this statistical property. So let's talk again about the potentials, the dual problem. Here again, epsilon, I take it to be 1. So the dual problem looks the same as before. It's just what was the exponential function now is a different function, which is called psi. And psi is the convex conjugate of the function phi that defines the divergence. And the conjugate is taken over R plus, not over R. Again, any optimizers of this are called potentials. They're usually not unique. I just call them potentials anyway. Again, there is a primal dual relationship. It involves the first derivative of psi instead of the exponential. Okay, when you have the exponential derivative, it's also exponential. You don't see the difference. Okay, so here it's the first derivative of psi gives you the density through this f plus g minus c as before. In general, now this is not invertible. So if you know the potentials, you know the density, but the reverse is less clear. So it's going to be important what that psi prime is. So if I do the LP that I'm interested in, then the conjugate or the derivative of the conjugate is this thing here. Okay, so now we need to slow down a little bit. So P, this is like LP and Q spaces, right? So you know that what is the dual of LP is LQ, and the P and Q are related in this way. So you get for the derivative, the exponent will be Q minus 1, and then there's this plus here, which is the positive part function, which can be very important. Okay? So this psi prime function, or psi in general, is constant on the negative half-line. The derivative is 0 on the negative half-line. Why is that important? Because this means that if the argument is negative, the density will be 0. So the support of the optimal measure will be the set where the argument here is positive, because psi prime is going to keep it positive. Whereas if the argument is negative, psi prime is going to map it to 0, and there's not going to be any math there. Okay, so the fact that this gets to have 0 value is closely related to the fact that you can have sparsity. If it were positive, there would be no way to have any set that has 0 measure. Okay, so some examples to see what we actually get. As you know, if P is below 2, then Q is above 2, and vice versa. Okay, so for instance, P is a 3/2, M psi prime is positive part of S square. So it looks like this. Straight to 0, and then like a parabola. Okay, the psi prime. So the first derivative here still has the good condition. So here, psi is in a C2, and the second derivative is in Lipschitz. Okay, if P is 2, then you get the ReLU function for the first derivative. So this function is Lipschitz. It's not differentiable at 0. So here psi is a C11. If you increase P further beyond 2, then the regularity decreases. First derivative starts to look like this. Okay, so it's further, but not differentiable, not Lipschitz. Okay, so in general, psi is always C1, and sometimes more, sometimes not more. Emphasizing it because it's going to be important later. So P between 1 and 2 are the good guys. When P converges to 1 with the correct rescaling, the divergence converges to the entropic case. So when P goes to 1, you should be better. Okay. Let me mention the dual problem is not strongly concave. Why? Because if this guy is constant on a big part of its domain, then it's just not going to be even. It's not even going to be strictly concave. In fact, the non-uniqueness also, if you have strong concavity, it should be unique, it is not unique. Okay, so that part went out the window. Unfortunately, the uniqueness went out the window. That's less tragic for me. You can still write a first order condition, of course, which now has the psi prime. I don't really have time, but in principle, you can again ask, is there a thincore time algorithm? Which now you would potentially have to solve this implicitly, but actually it's not too bad because it's a monotone line search, you can do it. There are some tricks actually to make it explicit, and then it turns out is iteration which is as simple as synchron, at least for the quadratic one. And it turns out the computation is much better than we expected, but that paper is not finished yet. But will be finished in a few weeks. So doing the differentiation of this, okay, now you just do the implicit differentiation, right? You think of the function theorem, you differentiate both sides by x. What you get the psi double prime of this times the inner derivative equals 0, right? You reorganize, okay, so formally, the derivative of f is something integral of second derivative of psi of this argument that you pick up the first derivative of the cost, some normalization of it. Okay, so formally, if you believe, f and g should be nice, so this part here could be nice, then the first derivative of f is still going to have the second derivative of psi. So even if c is smooth, somehow, okay, this is going to vary, and it's going to have positive or negative values, quite likely, then it's going to feel what happens with psi double prime at 0, and that is where the kink is. And for that reason, really, like f is not going to be smooth the way it was before. F is going to be as smooth as the first derivative of psi, and generally not more. Maybe if this is a continuous measure, from the fact that you're integrating over y is going to regularize, and that's true at the population level. Okay, but for the empirical problem where, this is just a couple of point masses, that's not going to regularize. So in terms of regularity that's uniform in the marginals, really, it's not going to be better than psi prime. So that's important for sample complexity. Okay, and that's why I was somewhat sketching the proof before, right? So in terms of sample complexity, the naive result is that somehow the regularity of psi is going to feed into the sample complexity. Okay, and that's okay. I recall here first the notation. You take i.i.d samples from mu and nu. Mu and nu-n are the corresponding empirical measures. You look at the corresponding empirical problem, which is the plug-in estimator. Its optimal coupling is called pi n, and the potentials are called fn-gn. Okay, so the prior result in this paper of Baraktar and co-authors is sort of what I said. So you look at this, you do the empirical process argument that I sketched before, which sort of analyzes, you use a priori bounds, how much can you limit the class that you're swooping over, and that gives you a result. So let's take the cost to be smooth, C infinity, and put the assumption on the psi. If the psi is ck, that sort of argument gives you an upper bound, which is n to the minus k over dimension. Okay, if k is infinity, you can get rid of the dimension dependence, but typically not. Okay, so that's kind of interesting that later I'll focus on psi being C2, so k is 2, then this is minus k 2 over d, which actually is exactly the same result we had in the very beginning. So according to this bound, like the regularization we put actually doesn't help at all relative to the unregularized problem. So then why did we do it in the first place? Okay. Now, this is one of the few instances in math where you have a lucky surprise. This is an upper bound, but there's no statement about it being sharp. Okay, so that's where our work starts. So turns out that actually the rate is not dimension dependent at all. Actually, all objects converge at the parametric rate. And even we have CLT, which is a big surprise because we don't have the smoothness and we don't have the, the PL inequality or whatever sort of nice convexity that we would like to have in the dual problem. Okay. 5 more minutes to tell you what the results are, and I'm going to be slower and rigorous. So what are the conditions? For the marginals, mu and nu, we assume they have compact supports. and one of the supports has to be connected and nothing else. Connectedness is important to get uniqueness of the population potential. If you want to have something which says that you converge, then you better have uniqueness in the limit. Otherwise, you don't really have a good hope of converging at all, let alone at a particular rate. Okay, they don't have to have densities or anything, to my surprise. So it's like if they're living on manifolds, actually it's covered because you just embed the manifold in RD. Okay, I don't want to see the follow-up paper which says we extend this to manifolds because it's already there. You never know. For the cost, we assume it's C1. Don't have to assume actually any geometric property of the shape here. And for the divergence, here is where the actual assumption is. Okay, everything is blah, blah, but the relevant assumption is that the conjugate is C2. The conjugate is C2, and that's what we're working with. Okay, so looking again at this discussion, this was the first derivative. This is bad. This is borderline, but not included. And this is good because the first derivative here is still differentiable. Okay, so among the Tsallis or LP regularizations, what we cover is P between 1 and 2. Well, 1 you could include because it's EOT, but it's already known, so we don't care. 2 is a boundary case that's not included in the slides. We think we can do it, but then have to assume more structure here and here. It's going to be a follow-up paper where P is 2. C1 is almost C2. You feel you're close, but actually it's quite delicate. Okay, anyway, so here we try to be quite general in terms of the cost and the marginal. So you see it's not some magic algebra that's going to drive the results. It's going to be something a bit more fundamental. Okay, so there's going to be 3 CLTs. Why? Because there are 3 key objects. The first key object is the cost. So this is the population cost, optimal transport cost. Here we take the i.i.d samples. This is the plug-in estimator. And the statement is that this is asymptotically normal at rate root n, so it's standard CLT. And okay, if you want, there is some formula for the variance of the limit, and it's related to the population potential. So if you know the population potentials, in principle, you can do this variance. You don't have to worry about the formula. The important thing is that this has a limit that's non-degenerate, which tells us that at least when this is non-zero, basically the rate is really exactly into the -1. Okay, potentials. There's also
the variance term doesn't depend, and that variance term is everything is separable, right?
Everything is.
So I mean, for assuming that xy follows the product matter, doesn't matter, right? Just margin factors for that particular run. You run xy following the product matter, but actually what you need is x follows mu and y follows.
Yeah,
that's exactly what you need, right?
Actually, so this actually because the cost, but only through the cost. And then,
right. Well, actually, the first 2 terms are additive, so you need a bit of covariance there. Sorry, yeah.
Yeah, so here you get the
covariance.
Yeah, I'm sorry, it's like I say variance of, so you should now take the variance of this whole huge expression, which makes it. Okay, so this is thankfully this is a scalar quantity, so you don't have to think about what asymptotic normality means, right? The potentials are functions, so it's some infinite dimensional kind of CLT. Okay, so I spare you here what the limit is. But the statement is that up to modeling out the constant, because you can always move a constant between f and g, so take some equivalence class to get rid of that. Then again, this object is asymptotically something in the right sense. Okay, so here is weak convergence over the space of continuous functions. This uniform norm has some limit, and I'm not sure, it's probably not very important what the limit is, but if someone asks, there is a slide here which tells you exactly what the limit is. Again, it's somehow given in terms of some Gaussian brushes, and the population potentials are the object that determines everything. Okay, so potentials, then the other thing is the couplings. For the couplings, they don't really live in a good space, so I don't know how to say CLT for couplings really directly. So the thing to do usually is you evaluate at a test function, which here it can be any bounded measurable test function eta, then you integrate it, and then this is the scalar, right? And then again, this scalar is asymptotically normal with a variance that has some expression. That's not written here, but it's written here if you care. I can skip this. How much? You can go for 5 minutes. Yeah. So numerical experiment is going to be limited for a reason. So I'm not trying to show, well, I love this like machine learning papers where you prove something and then you show the numerical experiments where you confirm what you already proved. So that's not necessarily what I have in mind. So here, what I'm going to see is a bit like compare the p=2 case, which we didn't quite cover, with the case that we actually did cover. Okay, so if you want to see the speed of convergence really, asymptotically, you need to be able to compute very precisely the limiting object. Okay, for EOT, there is closed form solution when the marginals are Gaussian. So that's usually the case that's looked at. For other regularization is actually, I'm not sure there was a known example with closed form solution. So we have one, but it's a bit degenerate. It's on the flat torus, and both marginals are the same. And the cost is the square distance cost on the flat torus. Okay, so mu equal nu, you have to grab the cost. Actually, for the unregularized problem, the solution is the identity map. It's kind of trivial. And it turns out that under this particular structure, there is closed form solution or semi-closed form solution where the potentials are, you can take them to be equal and equal to a particular constant, which is covered by this equation here. Okay. So here, because the population potentials are constant, like when you go back to these expressions that some of them I showed, some of them I didn't, actually in the CLT, the limiting variance is 0. So that normal is a degenerate normal. That means the speed of convergence can be faster, is expected to be faster than the n to the -1. But honestly, this is the only example where we can compute the limit sufficiently well to really see what's going on in the asymptotics. So here, what do you see here? So this is the number of points. This is log plot of the absolute difference between the sorry, this should be ROT. Not sure what happened here. Between the empirical problem and the theoretical problem. This is dimension 1, this is dimension 5, this is dimension 10. And at the top, the divergence is the 1.5. So that's a nice case. It's really covered by the theoretical result. The bottom line is a p=2. It's almost but not quite covered by the theoretical result. What do we see here? The slope is around -1, -0.8. I would argue that the dimension really doesn't matter substantially. And I would also argue that p=2 and p=3/2 actually behave quite similarly. When we did this, we didn't know how to prove the p=2 case. Yeah, it seems that there's some ideas. Okay. So as expected, it's actually faster than 1/2. If you can find an example where has somehow non-trivial limit and you can compute it explicitly, that would be quite valuable for a number of open questions. Okay, so this is the numerical experiment that I have here, because anyway, the theoretical result, to my surprise, happens to be so complete that there's not too much to ask in terms of numerical stuff that you haven't actually been able to prove. Okay, here's my conclusions. So firstly, if you don't remember anything except that, is that if you do LP regularization of optimal transport, you get a sparse approximation. Provably. Okay. The second takeaway for me is that, okay, so these non-entropic divergences have sort of bad reputation as being maybe computationally feasible. So what happened and actually Mickey Cooper is here, so he has one of the papers with Stephan Eckstein. Well, you look at the dual problem, and then you just attack this by, for instance, neural networks to parameterize the f and the g, and then you can maximize it. So numerically, that works surprisingly well. But in terms of analytic tractability, I think the reputation was kind of bad, but it turns out it's better than you think. At least that's my experience. The sample complexity is so much better than we ever hoped for. I didn't show you the computation, but actually it turns out the synchron style algorithm has the same exponential convergence as for EOT, which to me is also completely mind-blowing because there was no strong complexity to hope for that. And I would generally say there's very limited theoretical literature on these problems. and quite a few interesting open questions. And it turns out that it's analytically tractable, not in the sense that you have closed door solution for things, but analytically tractable in the sense that you can actually prove stuff, which previously was also not clear to us. Yeah, so that's it. That's what I got. Thank you.
Okay, we got about 5 minutes for questions. So is there any questions?
I think like for you show two versions with regularization. Just wondering if of interest to study the non-regularized optimal transport, the discrepancy between the non-regularized optimal transport and regularized optimal transport at the population level.
Yes, of course. Yes. So there's a.
But you don't show any results like that.
I didn't show any results because that's not the, so yeah, there's a quite substantial literature on this. Definitely for the EOT and a little bit also for the other. So there, of course, I shouldn't write the epsilon equal to 1 because you're interested in setting it to 0, right? So I guess the first question is, if you do this with epsilon, how far is this from OT, right? Yes, and so for somewhat general divergence, yeah, we know the convergence rate. It's in a paper of Stephan, Eckstein, and myself. In a very recent work of my co-author and two others, they even look at like the higher order term, and it's quite interesting, this expansion. There one starts to see that this LP regularization are related to porous media equation. So there are some results there. The coupling, I guess we have a mental image of how it approximates, but not a fully rigorous image. Yeah, for EOT, the literature is quite substantial. So yeah, we do know a few things, but also some important questions are kind of open still. Like, I guess, because let's say algorithmically, you would think about your discretizing measures, you get to choose the epsilon, you get to choose how many iterations you run. So ideally, you understand the joint picture, which tells you like how to actually do this computationally. So there are a couple of things which work algorithmically and are partially some better, some less understood. But yeah, absolutely, it's an interesting question that I didn't address at all. Just to focus.
Yeah, thanks very much. Do you have some intuition why the rate in the sparse regularized case is dimension independent? So because that's is there some intuition?
Not really. I guess the feeling is that sort of close to the population optimizer, things are like nearly as nice as you would hope they are. So like it's not strongly concave, but maybe quite close to it in certain directions, which happen to be the relevant directions. I don't think I have a precise intuition actually.
And related question, since the rate is dimension independent, could you perhaps extend this method to infinite dimensions, say between the ground motion and the solution of the stochastic differential equation? Or would there be a constant which might go?
Presumably the constant in front of the rate is dimension dependent. I mean, here it's definitely we use the finite dimension. But yeah, I mean, this is obviously a bit of the first paper, so like I'm not sure that this works in infinite dimension. Although for EOT, actually, if you accept the relatively bad constant, so the one for bounded costs, this actually really has complete dimensional independence that can be written by reasons. Surprisingly.
So I was wondering, just seeing the formula on the variance, whether that the same variance works also if you change your reference measure from the product to something else, would you get a similar CLT type of result? Say I'm not using the product, but I'm using another coupling.
That would change the structure of the problem.
So you don't think similar result would be expected?
Even the problem, okay, so for the entropic problem, something funny happens because of the shape with the log and stuff, that if you change this into another measure, which is also a product measure, say mu tilde times nu tilde, with the correct equivalence or absolute continuity, the solution coupling is the same. So you're changing this in by a constant, which is about the relative entropy between the tilde guys and the non-tilde guys. So there it's tractable. But if it's not a product measure, you're doing something completely different.
So is there a hope to choose a different coupling as the reference so that my computational or convergence rates are better?
I mean, convergence rate better, yes, but likely then you can compute it in an efficient way. Of course, it is true that if here you actually take the optimal transport, you will converge it one step, right? But then probably you can't compute it. So this is kind of having a product measure here.
So maybe the question is slightly different, that is there a way to prove that choosing the product measure is actually optimal in some sense? So no other choices should be considered at all.
You can consider other measures, and it makes sense in certain contexts, like in the Schrödinger bridge literature. I think it's just not as tractable. I mean, for this, Lebesgue measure is also a choice that is used, but it's a product measure. Non-product measure in this literature, you don't really see it. Yeah, there are other questions that pop up when this is not the product measure, like when the reference measure has smaller supports, then some things actually do go out the window.
Thank you.
But in the computational literature, and if you try, then yeah, well, that's nice. I mean, if you have the point of view that you added this to make your life easier, then you get to choose what you do.
Right, but I was thinking about what the theoretical result make sure that this is the easiest choice, or is there a way to formalize what you just did? What it did, it just makes perfect sense, but I was just thinking whether there's a theoretical way of justifying it.
Very theoretical, I don't know.
Okay, so we're a bit over time here, so we're ended there. So can everyone join me in thanking Professor Nutz again?